We'll get it back to you.
Right. So this is the title of my talk, but which is Technical Limits of Penetration of Asynchronous Wind and PV Generation in AC Interconnection. I'll come back to it in a second, but really what I want to start with is some motivation why I'm here, and hopefully why you are here listening to what I say. So it's about maths and energy, why myself, a power engineer, I'm talking to mathematicians, and why mathematicians wish to talk to me. So why mathematicians are needed? From my point of view, of course, there are some greater reasons why mathematicians are needed in the world. But from my point of view as a power engineer, math has always been there, and all solving optimization problems was part of power engineering. Part of my particular expertise is stability analysis of power systems. That's dynamic systems, and obviously mathematics was part of that. So it was always there. But why is this now increased interest of mathematicians in energy, and why you are here? Why we have a workshop over here? Well, the reason is obvious. It's because of the impact of the changes of the last 10 years or so, with the impact of stochastic distributed processes, renewable generation, and that calls for new skills and skills of professional mathematicians to help us power engineers to solve the problems. I mean, there are many friends, my friends power engineers, who think that their maths, which they acquired at the university doing the engineering courses, is good enough, maths and stats, to solve those problems. I'm more humble, and I believe that we engineers do need professional mathematicians to help us with their problems. And the main reason is, well, there was a quote from a less famous philosopher than Donald Rumsfeld, which was quoted in a few minutes ago. So, well, I can say after Socrates that I know that I don't know, which means that I know then the problems which are posed from the power system operation point of view by renewables with their stochastic and variable characteristics. I know the questions, but I don't know the answers, and that's the reason I'm working with mathematicians. And I hope they will help me to do it. And well, to some extent, well, it is self-defeating from my point of view, because one of the first mathematicians I started to work with is Chris Dent, who started with me working about 5 or 6 years ago. And I was hoping that he would help me answer a number of questions. And our 2 papers, the first papers which we published, it was the questions I was struggling with. I had been struggling with for a long time. When Chris came along, he just solved it in no time at all, and we published papers. But the bad news is that it was 5 or 6 years ago, and now Chris has educated himself that he can almost pass on for a power engineer, and he can pose his own questions, and he gets his own answers. So I need new mathematicians to help me, who are more ignorant, basically, about power engineers, and I can be of any use. Because I cannot be of much use for Chris, because as I said, he knows it almost all. So why I view my role in this whole debate as the keep it real. Again, there's a danger that I've seen quite a lot, especially in the United States. If you go to institutions like MIT, Caltech, not Florida, obviously, no, not Florida, Stanford and other places, they have, of course, top people in the world, top mathematicians in the world. They have discovered energy about 5 years ago. In MIT, this energy initiative, everyone is talking about it, but they haven't got a clue what they are talking about, because they have closed down or never had electrical engineering departments. So they don't have in-house electrical power engineering expertise to have a deep knowledge of the problems they are trying to solve. And I have seen a number of, I don't want to mention names, but I have seen a number of efforts by really top-class mathematicians who are solving problems which are in their heads rather than the real problem. So I see my role here, keep it real, man. So that's why my talk will be about, to a certain extent, educating mathematicians about real power engineering problems. And to some extent, it is the role I've been playing for some time. I mean, I was in DEC for 7 months last year, and I spent most of my time educating civil servants, again, about power engineering, because when they're trying to implement electricity, well, the device electricity market reform, it's good to know how electricity works, actually. So I see a lot of my role about education. So what my talk will be about is And it is hard engineering talk. There'll be no equations, there'll be plenty of diagrams, but I make no apologies for that because, as I said, I see this my role to help you educate how power systems work, and then you can solve real problems rather than imagined problems. So the content, so what I'm talking about is what are the hard limits to high penetration of wind and PV of renewables in the power system. And when asked that question, people always think about the balancing challenge. Wind goes up and down, we don't know how much, so we have to keep it in reserve, and then people think that's the main challenge. But it is not a technical challenge, it is an economic challenge. Because we know how to balance the system. Power system operators have been doing it for 100 years. You can use open cycle gas turbines, you can use storage, you can use customer demand response, you can import power from interconnectors. So it's the question, what's the best balance of all those different means? But it is not a limit for penetration of renewables. Theoretically, you can have 100% penetration of renewables. It would be horrendously costly, but you could do it. It's just a question of economics, not the question of technical question. I'm asking what is the real hard engineering limit to penetration. And so I'll be using results from Ireland. I'll show you in a minute why Ireland and some political policy implications for GB and other countries. So when I'm talking about limits, about grid integration of renewables, there's been plenty of reports published all over the world. These are examples of some of them, mostly from the United States, but also from Ireland over here. But the problem is that when they never touch about the problems I'm talking about. Mostly they concentrated on the challenge of the economic challenge of the balancing challenge. And those problems are important for the large interconnected AC networks, because continental Europe or USA, they are very large networks. We have all the different control areas, they call it Americas, or countries as we call them in Europe, which are interconnected and they can help each other. The problem which I'm particularly, and then countries like Spain or Denmark, they have very high penetration of renewables. Denmark, I think, is the world record. But they can do it easily because they can lean on the neighbors. They have good connections to surrounding countries, and they can use the neighbors to help them. Not only in the balancing, from the point of view of the balancing, but also from the point of view of technical integration, which is the main thing I'll be talking about. So this is United States, which is divided, which is the middle one, which is divided in 3 control areas, and there are different countries in Europe. However, if we look at GB, where is it? GB, Ireland, or Texas, these are separated islands which are connected by DC links. I'll come back to it. Why is it important to other countries? And with not only limited interconnection capacity, which means you cannot lean on the neighbors, but also means there are separated AC islands, like GB and Ireland or Texas. And that means that from the technical point of view, you have to look at it as the whole interconnection, rather than Europe, where Denmark is a very small part of the whole interconnected network in Europe. And it's important to look as a percentage of renewable energy sources, not for a given country, but as a percentage of the whole interconnection. So, for example, this is UCT, which is Europe. It is the old name of the Association of Network Operation. Now it's called ENSO. Anyway, so this is the total size of the generation. So UCT is big, Ireland is small. This is total installed wind capacity, which again is big, Ireland is small. But when you look at wind as a percentage of installed capacity, UCT is small, but Ireland is big. So Ireland is actually more important indicator than, let's say, Denmark, because Ireland has to manage it all on its own. Well, here will be peak, yes, of course. Instantaneous will be different, which I'll come in a second. So, of course, Ireland is our neighbor, and but they are very similar. We are both synchronous islands. It means we are connected by DC links to other countries, but basically Ireland is an excellent lab for us, because they have already, sometimes at night when there's strong wind, low demand, and instantaneous wind infit may exceed 50% of generation, which is a huge number. We are way away from that, but this is indication of problems where GB may face in about 10 years' time, maybe 20 years' time, depending how the plans pan out. So my point is, learn from the Irish. They're kind of like a lab rats for us. We'll see how the things go. And what I'm going to talk about is the report which they've published, I think, last year or 2 years ago, and they indicate some of those technical problems I'll be talking about. So one of the things, let me start from it, and then I'll explain why is it. So they have come to the conclusion that from the technical point of view, they have to spill wind, basically disconnect wind power plants, when wind is above 50% of instantaneous demand. They reckon they can push it up to 70%, but that's it. So that would mean there's a hard engineering technical limit of 50 to 75%. So what I'm going to talk about is why is that. So forget about the balancing problem, is the hard engineering limit, which is to do with frequency, which was mentioned a lot about, and it's to do with dynamic stability. So the question is 50 to 70% a hard technical limit, which you cannot break, and what are the ways around it? And for that, I need to go back a little bit to explain my educational hat on some fundamentals of power system operations so that you understand what those limits are and why they are there. It's important to appreciate that the power systems have been around for over 100 years. I think it was Westinghouse with Tesla who developed the first AC systems. And the most important from the technical point of view, that the operation of power systems was based around synchronous generators, which are those big machines running in power stations, and they have certain characteristics. The most important characteristic is they are synchronized. They're running together at the same speed, so that's why we have 50 hertz in the sockets over here. In the States, is 60 hertz. And this synchronous operation, which is due to the using synchronous generators, is absolutely essential for power system operations. That allows us frequency control, transient and dynamic stability, and manage voltage stability. I'm going to explain in a few words what's happening. So now the impact of replacing traditional power stations with new wind or solar, which are asynchronous, not synchronous, has a profound effect. So let me go for that, to explain that. And remember, that we need to consider the whole AC interconnection, which means that the whole Denmark can be wind or whatever, but Denmark still has next to it connected France with a huge fleet of nuclear generators, which are synchronous generators. So they don't have those problems. But if Ireland goes for that, they'll have a problem. So there are two aspects of it. It's dynamic stability and it's frequency control. So let me start from the first frequency control. And Sean had a test. So let me do a little test on you. I think majority of people will know the answer, but let's try it anyway. So the frequency control, how to maintain a power balance. It means generation is equal to demand in an AC, the whole AC interconnection. There is no storage. Generation must be at any time equal to demand minus losses. So in this time scale of minutes to minutes, is the markets will take care of it, and the system operator, national grid in this country, will make sure the demand is equal. So the generation is equal to demand. But they need minutes for it because power stations need some time to respond to their control signals. And so this is the daily demand curve with the merit order showing you how different types of power stations come on and off depending on how demand changes. But the question is, how is an instantaneous power balance maintained when the large power station, let's say size will be, which is the largest nuclear power, which is the largest part on the plate, in the country trips, and it can trip suddenly. So it means from 1 microsecond to the next microsecond, how do you maintain the balance of power when the demand is more than generation because you have lost power station. But the lights stay on, nothing happens. Demand is not equal to the generation, lights stay on, so where does the balance come from? That's my test. Oh, no, you are not allowed to say, no. Mathematicians. Yeah? Yeah, probably not a mathematician. So the answer is thought that what I said, there is no storage in the system, is actually wrong, because there's quite a lot of storage in the system, and it is the form of the inertia of all the rotating masses. There are huge generators, a lot of rotating mass, so there's a lot of kinetic energy stored. Sorry, I have one equation. I forgot I have one equation, which is the kinetic energy stored, is equal to the inertia times rotational velocity squared divided by 2. So that's proportional to inertia. To the inertia, it's proportional to the square of the speed. So what happens is that kinetic energy stored in all the rotating masses provides a cushion against momentary imbalance of power when we lose large power station or something like that. So now, the process of maintaining the balance is the primary frequency control, and then there is secondary frequency control. Primary frequency control is what happens immediately after you lose the large power station. And this is a nice picture which I've nicked from Mark O'Malley, which is a mechanical analog what's happening in the power system. So we have many generators which rotate and produce electricity. So we can imagine the mechanical analog is those gentlemen on a tandem, there are many of them, and they're pedaling in synchronous. They're pedaling together. So the analogy is that, of course, the speed of the pedaling is the same because it's fixed by the gear ratio. And the speed the whole bike is moving is the same. So this is like a frequency. So your question is, what happens when you lose large power station? It means what happens if one of the cyclists stops pedaling, takes the legs of the pedals? So that's obvious. Inertia will carry your bike up, but if the remaining cyclists pedal with the same force, it means power stations do not change their output, the bike will slow down until eventually stopped. So the inertial response is this first input, which basically means you still carry on, but the power input is less than the power output, generation is less than demand, so you need something else in order to make balance. The cyclists have to pedal harder in order to maintain the balance. So that's the part of the primary frequency control, which is restoring power balance by turbine response. So slowing down generators cause frequency to drop. So basically the cyclists will sense that the frequency is that they're going slower. It means they start to pedal faster. Push harder on the pedals. So the same thing is with the generators. They have so-called turbine governors, and those turbine governors traditionally they have been those watt centrifugal governors, which basically depending on the speed of rotations, those balls will move inside or outside. So those now of course it's all electronic. So those automatic turbine governors, they open more valves, more steam goes in or more water goes in, so that output of a power station will increase. And this will continue until the balance is restored, and that means that the frequency will stop dropping, but it will be less than 50 Hertz. So if we show it on the diagram, so this is what will happen. Initially, the initial slope of response is slope of decline is determined by the inertia of the system. Then the turbine governors start to open their valves, and then after some overshoot, we will have power balance restored. It means frequency is constant, and that takes usually about up to 1 minute. So it's pretty fast. And it's important that it's fully automatic and decentralized. We had this discussion earlier in the first session, what is the market, what is the role of the market, what is the role of control? Can you run the system in a completely decentralized way? The frequency response is completely decentralized. National Grid has no time, doesn't touch it. All the power stations in the system have those turbine governors, and they respond in that way. And now the important question is the inertia. This rate of decline that depends on the inertia of the system, and of course the bigger inertia, the bigger the system, the slower it will react to any changes. So that means if you have a very light system, very low inertia, that a loss of large power station will cause frequency to drop quite rapidly, and even it may trigger what is called frequency collapse, which means that the frequency will keep dropping because efficiency of power plants depends on the frequency. If frequency drops, they produce less power, which means that we have positive feedback process, and we would have a blackout. So it's absolutely important to maintain this frequency drop. It stops at certain value, and there are limits which are mandatory for National Grid and other system operators, and that depends on inertia, on the initial rate of decline. What happens afterwards is that you need to restore the nominal frequency, and then the system operator instructs power stations to increase their output In this country, it's manual. National Grid gives commands to particular power stations to increase output. In United States, in Europe, is AGC, automatic generation control, so the whole process is automated. So that is the whole process. So this is the primary frequency control, which is fully automatic, decentralized, and then restoring a frequency back to 50 hertz is centralized, manual, and automatic. So that process of frequency control is absolutely essential to maintain power balance in the system. And it's important that inertia plays a very important part for it. Another mechanical analog to this frequency control process is this slide, which shows you basically, so this is water coming in, this is generation, water coming out is demand. Water level is system frequency, so the system operator, when he sees the frequency drops, increases power output. So this is the fundamental. Well, the advantage of frequency, using frequency, is something what we've discussed today. You can measure it anywhere. It costs next to nothing. You don't to measure it. There are no communication links necessary. And the important thing is that DC links, which link, for example, Britain to France and Netherlands, separate the systems from the frequency response point of view, because the power is constant. The AC, it's not AC, it's DC. So that means that we cannot use European generators to help us when there is any problem in this country. And, well, there's the statement someone's made that AC interconnected systems are the largest machine ever built. Because if someone flicks light over here, the whole system in Britain will respond to it. So now, main topic. What is the impact of wind and PV on the process of frequency control on power system operation? That means we have less synchronous and more asynchronous generation. Because wind farms use induction generators, they are so-called double-fed induction generators, DFIC, which react very weakly to frequency changes. They react weakly to frequency changes. It means the effective inertia is much less. It's not inertia in the terms of the inertia, the mechanical inertia of the wind turbine. It is how it appears due to connect onto the system, due to connection, due to the way the whole thing works. And the reason is that we have here for the double-fed induction generator this additional converter, which tries to keep power output, maximizes power capture from wind, and that depends on the speed of wind, and does not react to frequency. So another mechanical analog, I quite like those mechanical analog to explain things to people. So again, if you look at so this is common shaft, the whole system, synchronous generators are tightly coupled to the common shaft. It means any frequency change will immediately be seen by all those generators, and basically all those generators contribute to the system inertia because they're coupled tightly. But induction machines are coupled by elastic links. It means although they do provide power to the system, but they do not react to frequency changes the way the synchronous generators do. So this is the effect, for example, from Ireland, the inertia drop, which shows that inertia will drop by 25% in 2020 compared to 2010. So this is the results of their studies. So that was wind. Now what about PV and also DC links and interconnectors? Now PV is connected by power electronics to the power system. It means it has no inertia whatsoever because nothing rotates behind it. So it's completely inertialess. That means it's very bad from the system response point of view. Similarly, as I said, DC interconnectors, they do not react to any frequency changes. So again, the power which is fed to Britain from France basically has no inertia connected to it. And this is a converter, one of the large converter stations. So the overall effect is lower effective inertia. So, as I said, the overall effect of lower system inertia is that the frequency drop following a large loss of a power plant may cause frequency to drop below the statutory limits, and even may cause frequency collapse in the most dangerous case. So, of course, there are some preventive measures. There are some ways of dealing with it. The most primitive measure, which Ireland does it at the moment, it restricts power generated by wind if it is above 50%, as I mentioned. What are the other mitigation measures? We talked about smart grids today, so let me briefly say a few words, things like Sean was talking about. One thing is synthetic inertia. The wind turbine has this additional electronics over here connected to the rotor, and basically what it can do, it can artificially slow down the turbine over here, and if it artificially slows down the turbine, that means that kinetic energy will be released and transferred to the power system. That means you can simulate the tighter connection from the inertia point of view with the system, so you can increase effective inertia provided by the wind generator. So that means you can do it. It is referred to as synthetic inertia. It's being at the moment tested by the manufacturers, but it has never been used to my knowledge. So we had this question this morning, whether those control means, this is part of the means which Sean was talking about, should it be market-based or should it be mandated? And I think there's a lot of discussion about, especially in this smaller power system, maybe equipping those wind turbines in those kind of controllers which will simulate the frequency response. Maybe they should be mandated, part of the grid code. So forget about the market. Let's give a power to control engineer who will tell you, you must do it. Forget about payments. Of course, there's a lot of discussion about it. Second thing, again, it was mentioned, fridges, HVACs, air conditioners, whatever. They can be equipped, of course, with some frequency the measurements. This is no problem at all, and they can be temporary, a few minutes halting of a cooling cycle. Remember, to stop frequency collapsing, you need half a minute, up to 1 minute, which means that from the point of view of the cooling cycle, it's not much. You are not asking for much. Basically, you are delaying this a little bit to give time to the system operator to commit more generation to reply to any frequency drop. And there's a discussion which, again, we've had a little bit this morning. The value to individual customers of equipping those devices would be next to nothing, because basically it would be a few pounds, the worst for individual customers. But if you take all the millions of customers together, that is a huge value from the power system point of view. So there's discussion, value to individual customers versus the public value. And again, discussions which we've had. So maybe because the value to individual customer is very little, maybe it should be mandated. Other mitigation measures is a frequency response. Again, I'm running out of time. So basically, you can have the controllers which are equipped here with the power system, which are DC links, which connect Britain with France and Netherlands. They may have additional controllers which can be used in order to borrow power from Europe if it's needed. So it means they would share frequency response with the continent, and I understand that National Grid is running some trials about it. Now, the next thing is so that was frequency response. The next thing is electromechanical stability, and that's ability to maintain synchronous generation. It is quite a complicated subject, and if you want to learn more, I would refer you to this book. You may notice the second author of that book, and there is all the knowledge you need to know about it. Quite simply, it can be compared, again, mechanical analog with balls bouncing up and down, and there's a question of maintaining synchronism, which means if those synchronous generators maintain spring-like synchronous torque that restores synchronism if something happens. We are talking about large synchronous masses rotating together. If there is disturbance, they start to oscillate, and that's the question of electromechanical stability. And if we have wind generators, again, they have the mechanism of creating the synchronous torque is completely different than that of the synchronous generators, and this is something which is very little research has been devoted to it, and we just don't know what will happen if there's a large fault in a wind-dominated power system. Maybe we'll lose stability. So coming to the results of this Irish study, they've published very interesting chart which shows over here. So here is the wind input to the power system, and as a function of the total load. And there are different areas which show safe area of operation and not. So at the moment they reckon 50% they can operate safely. they reckon with all those mitigation measures I've been talking about, equipping additional controllers, they can push it up to 75%. That would suggest that in the Irish case, the hard engineering limit of operating the power system as we know it, remember this is the current power system, is 75% of wind. So forget about balancing challenge, this is the hard limit. Well, is the limit the same in all power systems? Remember, this is just wind. Of course, PV would make things worse because it's completely inertialess. It's not a problem for Ireland because the last time anyone has seen the sun in Ireland was probably 500 years ago. But it might be a problem for some other system, especially Texas, to less extent Britain. So, because I was told to finish, so I will. So the conclusions, high wind and PV penetration pose significant technical engineering challenges due to replacing synchronous generators by asynchronous DFIC or converters due to PV. This is not a problem in large AC interconnector systems because in Europe you probably will always have a large fleet of nuclear generators in France, which will provide inertial response and maintain dynamic stability. But it might be a problem in the small islands like Ireland and GB. Ireland is an idle lab for us. Main problems, maintaining system stability following a large in-feed loss or network fault. Smart grids measures, there are fixes which make things help, but they will not solve all the problems. So perhaps we may need to redesign the whole system. I don't know. And the last thing is whether we should it mandated, forget about the market, or some market-based measures to address the problem. Thank you very much.
So maybe just a quick comment. If you promise it's quick, one or two, but we're going to miss out on our coffee break if we don't move on. And we'll have plenty of time for discussions with the panel in 20 minutes. So I can see one quick one.
It was about, I'd say, future services that could be provided in terms of inertia by wind turbines in the future. I mean, do you think, even if you say it's part of the grid code, they should be able to do it, wouldn't it be fair to give a reward to these turbines that provide the service?
Yeah,
there would still be some market value.
Well, there's this lot of discussion about it. As you can imagine, the wind generators wouldn't be happy about it because that interface with their production. Basically, they would get less revenues because they're optimized in order to capture as much power as possible from wind. Now they would have to do something else. It's unknown. I've been talking to representatives from wind lobbies, and of course they are very unhappy about those proposals, and they produce long papers saying why it shouldn't be done and all the and things like that. So this is kind of normal process. Lobbies fighting for their corner. So you need a central Ofgem or whoever who is the central referee who tells, forget it, we should do it because that's the public good. So we've mentioned it. The tragedy of the commons. We need it.
Okay, so discussion will be continued after coffee. Thank you again, Thomas.